Hi, this is Ed Sadowitz. Today I'd like to present to you what is effectively another solution to the measurement problem. Now, every foundational quantum physicist has a favorite solution to the measurement problem. Why do we need another? Well, most of the work to date on the measurement problem has been done with non-relativistic quantum mechanics. What I'd like to show is the perhaps surprising result that this can actually be made simpler using a relativistic approach. So we're going to start with just the normal formalism of quantum mechanics, that a state is a normalizable vector in a separable Hilbert space, and that a projection operator represents a proposition on that Hilbert space. Now, at this point, in a non-relativistic quantum mechanics, one would normally introduce Schrödinger's equation to get time evolution of the state in Hilbert space. But then one needs to introduce some sort of wave function collapse to deal with projection before continuing with further time evolution. For relativistic theory, on the other hand, we're going to take a space-time approach and introduce a representation of the Poincare group on the Hilbert space, and then a Hamiltonian that's invariant relative to that representation. But this Hamiltonian is not going to generate time evolution. In a space-time approach, the Hamiltonian instead provides a constraint on the physical states within the Hilbert space. And for a free theory, this constraint is just a mass shell constraint. And for an interacting theory, particularly quantum gravity, the constraint is the well-known Wheeler-DeWitt equation. That goes back to the work of Bryce DeWitt in the 60s. So this constrained Hamiltonian approach isn't new. What does that have to do with the measurement problem? Well, first we need the idea of a system. So we're going to represent a system as a complete orthogonal set of projection operators, where each projection operator asserts that S is in a certain condition. Now remember, this is a space-time theory. So the system you can think of as being, say, a space-time volume, and these conditions can be properties of the system perhaps on some time-like slice of that volume, or it could be over the entire hypervolume in space-time. And for simplicity, we're only going to consider discrete conditions. Now, if you have two such systems, they can be correlated for some physical state. Since we're not dealing with time evolution, that correlation is due to interactions that are packaged in the physical state itself due to the constraints of the Hamiltonian. The actual details of the dynamics really aren't important here. All that's important is that you can have a correlation such that if you check the condition, say, of the second state, then the condition of the first state is a function of the condition of the second state. If that function is the identity function, then you can consider the first state to actually be a measuring apparatus of the second state. What we really want to do now, though, is consider a system in the context of its environment in the universe. Now, no system is actually a closed system except for the entire universe. Systems of interest have to interact with their environment or we wouldn't know anything about them. We can think of the environment then as recording the condition of any given system. In that sense, the environment, in effect, measures the system, and some of the states of the environment reflect the states of the system. We can therefore have a joint eigenstate of the environment and the system that reflects this correlation. And then we can expand the state of the universe in terms of those joint eigenstates with specific coefficients. Now the question is, what are these coefficients? What we've gotten out of this correlation is, in effect, a decoherence of the system into these orthogonal eigenstates. Obviously, you'd like to interpret the coefficients as, according to the Born rule, getting a probability if we square the amplitude. Now, we could just assert that, but it's more interesting to see if this actually can come out of the formalism, which we actually do by making less of an assumption to start with. What we assume is that two states within this decomposition are equally probable if the amplitudes of their coefficients are equal. We can actually derive this with an approach that Zurek has talked about in several papers called entanglement-assisted invariance, or envariance. The idea is if an operation solely on one of two entangled systems can be undone by an operation solely on the other, then that operation shouldn't consider to have physical significance, since these are two separate systems even though they're entangled. In our case, that implies, where we consider the system and its environment, that changing the phases on these coefficients is not significant, because I can change the phase of the coefficient by applying an operation to the system, and I can undo that by applying an operation just to the environment. Similarly, if I swap the labeling of the conditions, say beta and gamma, that's not significant if the coefficients are equal, because I end up with the same state. All I've done is done a relabeling. And together, these two implications mean that it is not physically significant if you have two of these orthogonal states that have coefficients where their amplitudes are equal. And if you have two states where they are not physically significant, then it is reasonable to consider that those are equally probable descriptions of the universe. Now, from this, we can actually then derive the Born rule. First, we assume that the coefficients are the square roots of rational numbers, and that we have this m is the sum of the numerators for normalization. Then we introduce an ancillary system that breaks down these orthogonal states further, breaks them down into MA, M alpha substates for each of the alpha conditions. By normalizing those correctly and plugging that back into the state of the universe, the square root of M alpha terms cancel, and what we end up with is a sum of terms that have all the same coefficient. Therefore, each term is equally probable by the argument that we made previously, and since there are m terms, the probability is 1 over m. Now, given that the probability of one of these states is 1 over m, and each one of these states, when we group them together, the alpha condition is m alpha of those states, we just multiply the probability, and we get the probability for an alpha condition to be m alpha over capital M, and that is just the square of the coefficient. That's the Born rule. And we can extend that to irrational squared amplitudes by continuity. So now we've got the Born rule, but that Born rule is derived just for states of the universe. What we want to do is talk about next what it's like for us who actually have to live inside the universe. So assuming we have the Born rule for selecting one of the eigenstates out of this expansion of the state of the universe, now let's consider how we actually check the predictions of quantum mechanics. We do that by, for instance, making a bunch of identical experiments and then checking the statistics of the result and seeing if they correspond to the probabilistic predictions of quantum mechanics. So let's consider n identical experiments with n results. We can expand the state of the universe in terms of joint eigenstate of all of these, assuming these experiments are separated enough to not be independent of each other. And given what we talked about before, now we have coefficients, and we just multiply those coefficients together because these are independent subsystems. Then we can define the relative frequency of a specific result out of this set of results fairly directly. So we're taking a frequentist approach, which again has often been done in the context of the many worlds theory. However, the many worlds theory, this becomes difficult because if you just take a frequentist approach to define probability, then you sort of end up circularly going around and assuming probability in order to derive it. But what we've done is taken a different definition of what probability is to get the probability to state of the universe. Now we are taking a frequentist approach to look at the statistics within a specific general state of the universe. That means that this measurement of the relative frequency is itself an observable, and we can have an observation operator that reflects that observable, which again becomes part of the overall eigenstates that we can divide up the state of the universe into. And the expected value of that operator, when you plug in the definition of the relative frequency, is just the square of the amplitude of the result L. Now the key thing is, given that, which is based on the Born rule of the state of the universe, now we can look at the probability for measuring a specific relative frequency. And if we look at that probability and put it together, what we end up with is a Bernoulli distribution, and that Bernoulli distribution is peaked at this expectation value, which is just the square of the amplitude for the result L. That means that as n gets larger, it becomes almost certain that the result of this experiment, the result of checking the results of these identical experiments, is going to be consistent with the predictions of quantum mechanics. So what have we done here? We've talked about decomposing the state of the universe into eigenstates of the entangled systems in it. and then assigning a probability to each of the possible histories in this decomposition based on the amplitudes consistent with the Born rule. But instead of a normal many-worlds non-relativistic approach where you have a bunch of branches that happen in various times, this is a orthogonal decomposition, a decoherence of the universe over all space and time. So the probabilities here are the probabilities of a history of the universe. But when we look at the statistics of repeated experiments within the universe, they end up being as predicted by quantum mechanics. And we don't need to introduce any sort of collapse of the wave function or any sort of discontinuous mechanics to do that. We just need to introduce an idea of probability. What I presented today reflects work that I did earlier in specifically a space-time path formalism that can be seen as a specific interpretation to model what I've talked about here. Hopefully soon I'll have a paper out that boils the argument down to the simpler approach that I've talked about today. Thank you.